little bit of review before we pass out the quiz for you. So things like that. If I ask you to combine what you can combine there, what can we actually combine? The x's with the x's, the y's with the y's. Since it's all addition and subtraction, we can only combine things that have the same name. So the 8x combines with negative 3x. Remember, the symbol always goes with, the operation always goes with the number that comes after it. So 8x and negative 3x make 5x. Then, of course, we can combine the 5y and the 11y to get 16y. What's missing from my answer there yet? I need some sort of operation or symbol to connect the two numbers, so I put a plus in there. If that were a negative 16y, then it would be minus. Yep. Yeah, sure, let's do something like that. Let's do 3x minus 8z minus 5z minus 5x, sorry, minus 5x plus 2z. So here I've got the 3x, I'm going to combine it with the negative 5x is negative 2x. Then I also have negative 8z combined with positive 2z is negative 6z. So you've got the minus in there. It's always easier to remember when it's negative because you have to have the negative symbol there anyway. We might have 5x squared minus 3x plus 2 minus 8x squared plus 11x minus 7. So remember, we do these just like whole numbers. Our place values are x squared, x, and 1s. So we'll rewrite this 5x squared minus 3x plus 2. Then we'll rewrite the other number underneath it. The 8x squared goes under the 5x squared. The positive 11x goes under the negative 3x. And the negative 7 1s goes under the positive 2 1s. And we are subtracting down these columns. So 2 minus a negative 7 is 2 plus positive 7. It's a positive 9. Subtracting a negative becomes plus a positive. Negative 3 minus 11. So negative 3 minus 11 is negative 3 plus negative 11, which is negative 14, and of course x. So yeah, the plus here is because that was a positive 9. This is a negative 14x, so we already have the minus there. 5 minus 8 is negative 3, and we keep the name of x squared. Perfect. This is a positive 2. It's minus a negative 7. So positive 2 minus a negative 7. Remember, that becomes plus the opposite. So that's 2 plus 7. If we're multiplying, like 7x to the 5th, y to the 3rd times 4x to the 3rd, y squared. Remember, we multiply the counts. We do 7 times 4, which is 28, and then we multiply the names. X to the 5th times x to the 3rd, x to the 8th. Y to the 3rd times y squared, y to the 5th. When we're multiplying, we have to make sure we have the same base on our exponents. That's why we can combine the y's with the y's and the x's with the x's and the y's with the y's. When we're multiplying two exponents that have the same name, so have the same base, we can just add the powers. 5 plus 3 makes 8. Or we might divide. 42 x to the 9th, z to the 3rd, divided by 7, x to the 4th, z. So we combine the counts again. 42 divided by 7 is 6. Then we do each name separately. X to the 9th divided by x to the 4th, x to the 5th. When we're dividing, we subtract powers. Now the z to the 3rd divided by z, what power is on this z? It's a 1. There you go. So 3 minus 1 is 2, z to the 2nd. So we might have 5x to the third times 7x to the fourth minus 2x squared. This is where we distribute. Now remember, we saw last week we could write this out and do long multiplication just like we would with whole numbers. But there's that shortcut of distributing. 5x to the third times 7x to the fourth. 35. X to the seventh. Good. 5 times 7 is 35. X to the third times x to the fourth is x to the seventh. Now the second part is what we have to be careful with. That's 5x to the third times negative 2x to the second. The operation goes with the number that comes after it. That gives us negative 10x to the fifth. Good. And that's our result. We would have got the same answer over here. It just would have been like long multiplication. So 5x to the third times negative 2x squared. 5 times negative 2 is negative 10. X to the third times x squared is x to the fifth. Then we move over. 5x to the third times 7x to the fourth. 5 times 7 is 35. X to the third times x to the fourth is x to the seventh. Same result. This just looks more like our regular multiplication with whole numbers. That, remember we said, this is the full process of multiplying that out. But they have this shortcut that makes it a little bit easier to do. Something like this. We had said you could actually write that out and do the long multiplication there as well. It'd be 3 times negative 7, then 3 times 4x, and then the 5x times negative 7, and so on. What's that? The FOIL, you got it. Some books call it FOIL, some just show you how to do it. Anyway, the F shows us, stands for the first digit of each number. What's 4x times 5x? 20x squared. O stands for outside, so that's the 4x times the 3, which is 12x. And it's a positive, so I put the plus in front of it. I stands for inside or inner, so I would do the inside numbers. The negative 7 times 5x. Negative 35x. Now, since that's also an x, I'm going to put it under the 12x, so we remember to combine those. And L stands for last. The last digit of each is negative 7 times 3, which is negative 21. And then we'll combine negative 21. 12 and negative 35 make negative 23x, and then the 20x squared. Not so bad? Still better than a sharp stick in the eye? So something like 27 x to the fifth, y to the third, minus 45 x to the fourth, y to the fifth, plus 18 x to the third, y to the seventh, divided by 9 x to the third, y to the third. Remember, we saw examples like this with whole numbers last week where we just had 936 divided by 3. We could just divide each digit. 9 divided by 3 is 3. 3 divided by 3 is 1. 6 divided by 3 is 2. Same thing happens here. We can just divide each digit. 27 x to the fifth, y to the third, divided by 9, x to the third, y to the third. What's 27 divided by 9? 3. X to the fifth divided by x to the third. X to the second, we just subtract the powers. Y to the third divided by y to the third. It's just y to the 0, right? 3 minus 3 is 0. Y to the 0 is just 1, so we don't have to do anything with it. So next we're going to do the negative 45, x to the fourth, y to the fifth, divided by 9, x to the third. Negative 45 divided by 9 is negative 5. X to the fourth divided by x to the third. X to the 1, or just x, you got it. And y to the fifth divided by y to the third. Y squared, good. Finally, we go to the 18, x to the third, y to the seventh. 18 divided by 9, 2, it's positive, so I'm going to put plus there, plus 2. X to the third divided by x third, x to the 0, so it cancels out. Y to the seventh divided by y to the third, y to the fourth, and that's it. How about 7x plus 3y? What do I get? 7x plus 3y. Good. How about 5 plus 8y? What do I get? 5 plus 8y. Nothing we can do with that. Good. Okay, I'm going to pass out the quiz for you here quick. We'll go ahead and get started on our next piece. We're going to review a little bit of where we ended off, a little bit more of where we ended off last Friday, and that was converting into the scientific notation. And remember, the scientific notation actually came from those place values that were powers of 10. In our numbering system, all of our place values are a power of 10. One's place is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the third, 10 to the fourth, 10 to the fifth, and up the line. And their decimal place values are negative powers. So this is 10 to the negative 1, negative 2, negative 3, on down the line that direction. And when we had a number like 7,200,000, to put it in scientific notation, we found the first digit that is not a 0, that's the 7. And we're going to place the decimal point after it. So it's 7.2. Any of the trailing zeros at the end we can leave off. Then we name the place value of that first digit we found, that first non-zero digit. That's in the 10 to the 6th place. So 7.2 times 10 to the 6th is how that becomes scientific notation. If we have 0.00087, again, the first non-zero digit is the 8. So we're going to put the decimal point after that, so it's 8.7. And the place value of that 8 is the 10 to the negative 4th place. Now we came up with a shortcut for doing this. We have 48 million to put it in scientific notation. My first non-zero digit is the 4, so it's going to be 4.8. My decimal point started at the end, and it had to move over to here. How many spots did it move? 7 spots. This was a large number. It was bigger than 1, so that means it's a positive power of 10. So that's 10 to the power of 7. So 0.000000039. First digit is the 3, so it's 3.9. 1, 2, 3, 4, 5, 6, 7, 8. You got it. And yes, that was a small number. It's smaller than 1, so it's a negative place value, negative power 10 place value. Or going the other direction, 7.3 times 10 to the negative 4. We start out with our 7.3. The 4 on our power of 10 tells us the decimal has to move 4 spots. The negative tells us it is to the left. This is a small number, so we make it smaller. We go 1, then we have to add zeros, 2, 3, and 4. So 0.00073. We put a 0 up front. Or we might have 4.9 times 10 to the 5th. We start out with the 4.9. The 10 to the 5th tells us the decimal has to move 5 spots into the right since it's positive. So we go 1, 2, 3, 4, 5. So 490,000. So our first new topic for today is we want to look at doing operations with that scientific notation. And I'm going to review the rules when we add and subtract. When we add and subtract, of course, we must have the same name. With fractions, that was common denominator. With decimals, that was line up the decimal. With algebraic numbers, That was the same variable and power. Then, of course, we combine counts. And we keep the same name. The heck is that? Does it do that all the time? Okay. It does sound like there's something rattling around over there. I don't know if it's just the wind in a vent or what. If we had something like 3 7s plus 2 7s, those have the same name, so we combine the count. 3 plus 2 is 5, and we kept the name 7. If we had 5x squared y to the 5th plus 2x to the 3rd y to the 5th, could we add those? Careful. We don't have the same name. We have x squared next to the 3rd. They're slightly different. We can't add those. But if we had 5x squared y to the 5th plus 2x squared y to the 5th, now they have the same name. We combine counts. 5 plus 2 is 7, and then it's keep the same name, x squared y to the 5th. Scientific notation, remember when we did whole numbers, the name came down to the place values. We can only combine things at the same place value. In scientific notation, 7.3 times 10 to the 11th, what part of that indicates a place value? 10 to the 11th. That is the name. So, to add numbers in scientific notation, they must have the same power of 10. Now, in this case, that parentheses is not an enclosing symbol. It is just telling us that's a single number. It's like putting parentheses around a negative. So 7.3 times 10 to the 11th plus 2.1 times 10 to the 11th. We combine counts. 7.3 plus 2.1 is 9.4. And then we keep the same name, so it's times 10 to the 11th. Not so bad? (5.6) times 10 to the negative 9th plus 3.5 times 10 to the negative 9th. We combine the counts. 5.6 plus 3.5 is 9.1 times 10 to the negative 9th. We just keep the same name. Now, it's not always that simple. Sometimes we have to make some adjustments. You might have 4.8 times 10 to the 13th plus 7.4 times 10 to the 13th. When we go to combine counts here, 4.8 plus 7.4 is 12.2, good, times 10 to the 13th. We still keep the same name. However, when we get to this point, we see that there's a problem. Scientific notation can only have one digit in front of the decimal point. We have 2 right now. So we have to move that over to make it 1.22. There you go. This number got smaller by 1 place value, so our power of 10 has to do the opposite. It has to get larger by 1. So 13 plus 1 is 14, so it's 10 to the 14th. Be careful when we get into the negative powers. If I have 8.9 times 10 to the negative 8th plus 6.4 times 10 to the negative 8th. They have the same name, so we'll go ahead and add. What's 8.9 plus 6.4? Careful. 15.3 times 10 to the negative 8th. Yeah, right, we keep the same name for now. Now we do have to adjust. Move it over. There you go. The number got smaller by 1 place value. The power gets larger by 1. Negative 8 plus 1 is negative 7. A lot of people want to go the wrong direction on the negative powers. Yeah, if this gets smaller by 1 place value, add 1 there. If it got smaller by 2 place values, which we'll see later on, then you have to add 2. If it gets smaller by 3 place values, you add 3. What if our original numbers didn't have the same power of 10? Like 6.83 times 10 to the 9th plus 4.7 times 10 to the 8th. Well, we can add them, just like fractions, we can change the names. Here we can change the names so that we can combine these. Normally we stick, when we're adding, at least we stick to the higher power. So that'll stay 6.83 times 10 to the 9th. This one, however, has to become 10 to the 9th. What's that? Yes. The exact opposite of what we did up here. Here the power got larger by 1. The number gets smaller by 1 place value, so it is 0.47. So now we add 6.83 plus 0.47 is 7.3 times 10 to the 9th. The power stays the same. Any questions on adding? When we subtract, of course, we still have to have the same name. So I have 6.4 times 10 to the 13th minus 4.5 times 10 to the 13th. We have the same name, both are 10 to the 13th, so we subtract. 6.4 minus 4.5 is 1.9, there we go, times 10 to the 13th. Or 9.1 times 10 to the negative 11th minus 3.4 times 10 to the negative 11th. We combine counts, 9.1 minus 3.4 is 5.7, there you go, times 10 to the negative 11th. Again, it doesn't always stay that easy. We can run into things like this. 6.42 times 10 to the 13th minus 5.87 times 10 to the 13th. Still have the same name, but when we subtract here, 6.42 minus 5.87 is 0.55, right? Times 10 to the 13th. We keep the same name. Now here, all we have is zeros in front of our decimal point. So we've got to move it the other direction to make that 5.5. There you go. The number got larger by 1 place value. The power gets smaller. 13 minus 1 is 12. So send to the 12. This one's even trickier when dealing with the negatives. We might have 9.13 times 10 to the negative 15th minus 8.61 times 10 to the negative 15th. We subtract the counts. 9.13 minus 8.61 is 0.52, good, times 10 to the negative 15th. Now again, got to move that over. That's going to be 5.2. Got to subtract 1. Negative 15 minus 1 is negative 16. That's the one people mess up because of that subtracting from a negative. We don't always have the same power of 10 to start off with. We might have something like 8.13 times 10 to the 9th minus 6.4 times 10 to the 8th. Again, just like with addition, we usually change them to the higher power. So this one's going to just stay 8.13 times 10 to the 9th. This one's going to have to become times 10 to the 9th. Power got bigger, number gets smaller by 1.64. You got it. We subtract 8.13 minus 0.64. You got the right idea. 7.49. You did, Adam, yeah. Minus or times 10 to the 9th. There we go. They don't have the same name, so we just can't combine them. Or if we'd gone to 10 of both of them to 10 to the 8th. Okay, so this would become times 10 to the 8th. Power got smaller, number gets larger, so that's 81.3. Minus the 6.4 times 10 to the 8th. So 81.3 minus 6.4 is 74.9 times 10 to the 8th. So then we just have to move it back. So it's 7.49 times 10 to the 9th. We get the same result. It's just like with fractions. If you don't find the least common denominator, if you go for the bigger denominator, it still works. You just have to reduce at the end. When we multiply or divide numbers, we do not need the same name. So with fractions, this was we didn't need a common denominator. Decimals, we didn't have to line up decimal points. With whole numbers, every digit of one number combined with every digit of the other number. Algebraic numbers, the same thing. Every digit of one number combined with every digit of the other number. Scientific notation, same thing. We can combine, we don't need the same name. We're going to end up combining those names. So we combine counts. And of course, we also combine names. With algebraic numbers, if I had something like 7x squared y to the 5th times 4x to the 3rd y to the 3rd, doesn't matter that I have different names. I combine counts. What's 7 times 4? 28. Then I combine each name. X to the 2nd times x to the 3rd, x to the 5th, y to the 5th times y to the 3rd, y to the 8th. With my scientific notation, it works the same way. I have 3.2 times 10 to the 13th. You okay back there? Times 2.4 times 10 to the 5th. It doesn't matter that they have different names. We're going to multiply the counts. 3.2 times 2.4 is 7.68. Then we combine the names. That's 10 to the 13th times 10 to the 5th. 10 to the 18th. We combine the powers. We add the powers. So we can end up with some weird things with our powers. We have 4.1 times 10 to the negative 11th times 1.8 times 10 to the 7th. So we're going to combine 4.1 times 10 to the 8, or 4.1 times 1.8 is 7.38 times 10 to the negative 4. There you go. Negative 11 plus 7. Negative 11 plus 7 is negative 4. We have 5.3 times 10 to the 18th times 4.6 times 10 to the 11th. Well, we have the 5.3 times the 4.6. $24.38 times 10 to the Yes, 10 to the 18th times 10 to the 11th. We add the powers. 18 plus 11 is 29. Now, of course, you see a problem with this answer. What is it? Got to move the decimal. So that becomes 2.438, 10 to the 30th. Good. This number got smaller by one place value. The power had to get larger by one. Remember, each place value is multiplying or dividing by 10. That's why we have to adjust the power of 10. We might have 7.5 times 10 to the negative 21st times 3.8 times 10 to the 9th. So 7.5 times 3.8. 28.5, good. Times 10 to the negative 12, good. Negative 21 plus negative 9, you got negative 21, negative 21 plus 9. Negative 21 plus 9 is negative 12. Now, of course, we've got to adjust there. What's this going to become? 2.85 times 10 to the negative 11. There we go. This got smaller by 1. Power gets larger. Negative 12 plus 1 is negative 11. The negatives will haunt us. So the multiplication is actually simpler. You don't have to have the same names. You don't have to adjust them. You just go ahead and combine them, and you keep that same name. Division. (1.728) times 10 to the 8th divided by 1.44 times 10 to the 3rd. Again, we don't need the same name. We combine the counts. 1.728 divided by 1.44 is 1.2 times 10 to the 5th. When we divide, we subtract the powers. 8 minus 3 is 5. We might have, blacking out here, 5.76 times 10 to the negative 8th divided by 4.8 times 10 to the 11th. So I divide the counts. 1.2 times 10 to the negative 8 minus 11 is a negative 19. There you go. That's negative 8 plus negative 11. So negative 8, negative 11 is negative 19. Let's see here. (3.24) times 10 to the 13th divided by 3.6 times 10 to the negative 9th. So we'll divide the numbers first here. 3.24 divided by 3.6 is 0.9. Good. Times 10 to the, so 13 minus a negative 9. 13 plus 9 is actually positive 22. Positive 22nd power. Like I said, the negatives will haunt us. And of course, we still got to adjust that by, move it over, it's 9 times 10 to the 21st. The number got larger, the power gets smaller. So let's do 6.76 times 10 to the negative 18th divided by 5.2 times 10 to the 15th. First, 6.76 divided by 5.2. 1.3 times 10 to the there we go. So it's negative 18 minus 15. So it's negative 18 plus a negative 15. So negative 18, negative 15. Well, let's see, I come up with one more here that gives us, makes us adjust. Let's do 2.89 times 10 to the negative 12th divided by 3.4 times 10 to the 17th. So yes, 2.89 divided by 3.4 is 0.85 times 10 to the, there you go, negative 12 minus 17 is negative 12 plus a negative 17. So negative 12 and negative 17 is negative 29. Of course, we got to adjust. 8.5 times 10 to the number got bigger, power gets smaller. Negative 29 minus 1 is negative 30. Like I said, the negatives are something that haunts you throughout all of the basic algebra portion of stuff. When we had something like this, 4x to the 5th to the power of 3, we have to do the power of the count. 4 to the 3rd power is 4 times 4 times 4, or 64. 4 to the 3rd, yeah, becomes 64. When we do the power of the power, what do we do with the powers? Multiply them. 5 times 3 is 15. So that's 64x to the 15th. If I have 2 x to the 7th, y to the 5th, and let's go to the power of 9. I actually have to do 2 to the power of 9, which is 512. Good. And then for each of the names, we combine the powers. X to the 7th to the power 9. 7 times 9 is 63. Good. So x to the 63rd. Y to the 45th. 5 times 9 is 45. So we take the number to the power, and then we have to combine the powers on the names. 5, x to the 3rd, y to the 5th, z to the 4th. To the power of 4. 5 to the 4th power is 625. X to the 3 times 4 is 12. Y to the 20th, and z to the 16th. Any questions on how I came up with any of those numbers? Okay. When we do scientific notation, it works the same way. We might have 1.2 times 10 to the 8th to the 3rd power. We do the power of the number. This 1.2 to the 3rd power is 1.728. 10 to the 8th to the 3rd power is 10 to the 24. We multiply the powers. 8 times 3 is 24. Just like x to the 8th to the 3rd power would be x to the 24. So let's say we have 5.3 times 10 to the negative 9th. And let's take this to the 6th power. So 5.3 to the 6th power is 22,164.36, we're going to call it. We'll round it at 2 decimal places since we're going to have to move the decimal point anyway. Times 10 to the negative 54. Very good. Negative 9 times 6 is negative 54. Now we have to move the decimal point. It has to move all the way up here. So it moves 4 spots. Becomes 2.216436. Now the decimal point moved 4 spots. The power has to change by 4. The number got smaller, the power gets larger. Very good. So we add 4 to that, it's a negative 50. 4.2 times 10 to the 7th to the 5th power. What's 4.2 to the 5th power? We'll go 0.91. So 1306.91 times 10 to the 35. Good. We adjust our decimal point here. 3 spots, so the power of 10 becomes 38. Good. The number here got smaller by 3 decimal places. Power gets larger by 3. A root. The square root of x to the 8th. Remember, that's asking us what number squared equals x to the 8th. Well, x to the 4th squared equals x to the 8th because we simply multiply the powers. 4 times 2 makes 8. So when we do a root, we're going in the opposite direction. We're dividing the powers. It's not written here, but that's a square root. It's implied that that's a 2. That would be 8 divided by 2, so x to the 4th. So if I have the square root of 49, x to the 12th, y to the 6th. What's the square root of 49? 7. So we actually do the root of the number. How about the square root of x to the 12th? X to the 6th, y to the 3rd. Very good. If it's not a square root, if it's something like 4th root, we still have to do the root of the number. The 4th root of 81. Now there's a shortcut. If you can't find the n root button on your calculator, you can just do 81 to the power of, and then in parentheses do 1/4. The 4th root is the same as the 1/4 power. It is 3. It's doing it again back there. I don't know what that. It sounds almost like a diaphragm letting go and breathing, releasing pressure or something. So anyway, for the powers then, we divide by 4. X, so the 4th root of x to the 12th is x to the 3rd. 12 and y to the 5th. Good. 20 divided by 5, or 20 divided by 4 is 5. So when we look at our scientific notation, square root of 1.44 times 10 to the 18th. Well, what's the square root of 1.44? 1.2. And the square root of 10 to the 18th? 10 to the 9th. Yes, we divide the power by 2. We might have the 4th root of, oops, that's not what I wanted to click, go away. Let's see, 2.5 to the 4th power. Let's see what that gives me. That's not going to do it. .0736, I guess we'll have to use. The 4th root of 2.0736 times 10 to the negative 12th. So the 4th root of the 2.0736. Remember, if we can't remember the 4th root, you 2.0736 to the 1/4 power is 1.2. Times 10 to the negative 3rd. Negative 12 divided by 4 is negative 3. What do you think? Fun stuff? No? Oh, come on now. It is just a touch confusing. I'm going to give you a few minutes to get some work done here before we take our break. In the big book, I think I gave you these pages last week. The page 205, 612A, and 612B. I believe the pages were wrong too, weren't they? Page 212, exercise 613, A and B. Well, the pages of the operations, we'll see if I got these pages correct. Page 208 through 210. Somebody have the big book with, we can double check. Lexi's got it, good, we'll double check these pages here. This is exercise 6-12C. And page 213. Okay, so it looks like I'm probably gonna have to adjust my pages here. Let me come take a look at your book here. Let's look at it. Gotcha. Yep. So that one looks right. Let's see, 213, let's see if that looks right. That looks right as well. So those pages are correct. You guys have your books with so you can do a little homework? No? So we put the scientific notation in there just because the operations of the scientific notation so similar to our operations with the algebraic numbers. So let's go back to our algebraic numbers and our uses of variables. The one use that we have not looked at much yet is that known number, the single number that's just not known yet. Things like 3x plus 5 equals 29. Well, to work with those, let's start with a simpler example, like this. X equals 4. Now, of course, these are called equations, and in these cases, the variable has a single value. We just have to figure out what it is. Now, the key to these, of course, is that symbol right there, which is called the equal sign. If I ask people to define what it means, it typically becomes hard to define without using the term equals. Can anybody define what it means? The same as, same value as. That's a good word there. What's on one side has the same value as what's on the other side. In fact, you can think of it as a scale that's balanced around the equal sign. So what's on one side is exactly the same weight as what's on the other side. Now, all equations start out in this form, as a variable equals a number, and they're built from there to build onto an equation. We can use any of our basic operations. Remember, we've talked about them coming in inverse pairs. We can use addition and subtraction. We could use multiplication or division. We could use our powers and roots. And there are other inverse pairs that we won't get to in this class, like exponentials and logarithms, trig functions and inverses. If you do go on to the second class, you would get to the trig functions and their inverses in there. But there's a lot of other operations that could be applied that we're just not going to do in this class. So let's start out with something simple. Let's add 7 to it. So that's now x plus 7. Now, if we add 7 to one side, the scale is going to tip unless we do what? Add 7 to the other side. We have to do exactly the same thing to both sides. 4 plus 7 is 11. So we have now built a more complex equation. Now, typically, we're not asked to build an equation. We're asked to solve an equation. What we're being asked to do when they ask us to solve an equation is to take it apart and get back to that original form of a variable equals a number. Well, this equation was built by adding 7. How do we reverse that? Subtract 7. Very good. Subtracting 7 will remove that plus 7 to get x by itself. Now, if we subtract 7 from one side, we have to do it to the other side to keep our scale balanced. 11 minus 7 is 4. And that was the key. We have to get the variable by itself on one side and see what number is on the other. Here we got x equals 4. We took that equation apart. Now here we built the equation, so we knew how to take it apart. The key is being able to look at an equation and tell how it was built. If I have something like 9 equals x minus 4, to figure out how it was built, we first find the equal sign. Of course, that's right here. That's the equal sign. Second, we find the side with the variable. Of course, that's over here. And then we ask, what is keeping the variable from being alone, being by itself? Remember, we want the variable to be by itself on one side and a number on the other side. Here, it's the 4. And then, of course, part of that is what operation attaches it. What operation attached the 4? Subtraction. It was subtract 4. So the opposite would be to add 4. So if we add 4, it's going to remove that. Of course, we have to remember to also add 4 to the other side. So 9 plus 4 is 13. Equals, over here the 4 is canceled out and we just have x. So 13 equals x, or x equals 13. Or we might have 6z equals 18. What's keeping z from being alone? It's multiplied by the 6. Good. To get rid of it, we're going to divide by 6. So the 6 is gone there. Z equals 3. Not all of our equations are that simple. We have 3x minus 7 equals 32. So here we look at what has been done to our variable, what's done to x. Well, here's the equal sign, the variable's over here. We have both the 3 and the 7. The 3 was attached by multiplying and the 7 was subtracting. According to order of operations, which one gets done first, multiplying or subtracting? Multiplying. So when this equation was built, x was multiplied by 3, then the 7 was subtracted from it. Now, if you put something together, whether it's a piece of furniture, a model, maybe a toy, a shed, if you go to tear it apart, you just finished putting it together, you just put on the last piece. If you go to take it apart, what's going to be the first piece you take off? The last piece you put on. So here, the last piece put on was subtracting 7. That's the first piece we have to remove. What do we do to remove it? We add 7. That takes away the minus 7. And of course, we remember we have to do it to the other side as well. So what do we have here now? 3x equals 39. Good. Now we have to remove that multiplying by 3, and we'll do it by dividing by 3 to give us x equals 13. Good. Now, if we are not sure of ourselves here, we can always double check our answers. If we think our answer is x equals 13, we can go back to the original equation and rewrite it, replacing x with 13. So 3x becomes 3 times 13, then minus 7 equals 32. And check to make sure both sides equals 32. So the right side equals 32. The left side, 3 times 13 is 39 minus 7, bless you, is 39 minus 7 is 32. So we have 32 on both sides. We might have 2z plus 11. Let's see, 35 equals 2z plus 11. What was, first of all, done to z to build this equation? Multiplied by 2 and add 11. In that order. So to take it apart, the first piece we remove is the last one we did. So we will subtract 11. Giving us what here? 24 equals 2z. The 11's been removed. Good. Next, we have to divide by 2 to remove the multiplying by 2. So we do that to both sides to get 12 equals z, or z equals 12. Again, we can double check that. We're going to put 12 in there for z. So we got 35 equals 2z becomes 2 times 12 plus 11. So on the left side, there's nothing to do. That's just 35. On the right side, 2 times 12, 24 plus 11, 35. Not so bad. I'm going to have you guys try one on your own here. Let's do 4x minus 3. Come back here. 4x minus 3 is 21. I'll give you a half minute or so to work through that. So when this was built, x was multiplied by 4 and then the 3 was subtracted. So to take it apart, we will add 3 to get 4x equals 24, and then divide by 4 to get x equals 6. And again, if we want to double check it, 4x will become 4 times 6 minus 3 equals 21. Need to make sure we get 21 on both sides, because we have 21 on the right. 4 times 6 is 24, minus 3 is 21. So we're good. So here, we go to find our equal sign is right there. We identify which side the variable's on. It's on the left side, but it appears twice. Perfect. If we go back to the idea of the balanced scale, they're on the same side of the scale. So we can just basically push them together in one big pile, and it won't change the way the scale balances. We can combine the like terms, exactly. So 5x plus a negative 2x is 3x. We still have the plus 2, so it's 3x plus 2 equals 20. Now to take that apart, we would subtract the 2. Yeah, I know what you meant. 3x equals 18, and then divide by 3 to get x equals 6. And again, we can still double check that. Now we have to put in the 6 for both of those. So 5x becomes 5 times 6 plus 2 minus 2x becomes 2 times 6 equals 20. So the right side is 20. We have to make sure the left side is 20. 5 times 6 is 30. 2 times 6 is 12. 30 plus 2 is 32. Minus 12 is 20. So we do get 20 on both sides. What's different on this one? Yeah. The variable appears twice, but it's once on each side. I can't just push them together anymore to make a big pile because it would change how it balances. They're on opposite sides. So what I have to do is I have to get rid of one of them. Literally, like, grab it, take it, and throw it off. Mathematically, the way we do that is if it's positive, we subtract it. That gets us to 0. If it's negative, we add it to get back to 0. It doesn't matter which one we remove, whether we remove the 7x or the 2x. Typically, it's easier if we get rid of the smaller one. so that we don't have to deal with negative numbers as much. So yes, we're going to get rid of the 2x. Since it's positive, we are going to subtract it. Now, if we subtract 2x from one side, we have to do it to the other side. When we add or subtract, we must have the same name. So the only place we can take it away from on the left side is from the 7x. So 7x minus 2x is 5x. We still have the minus 8 there, equals, here the 2x cancel out, we still have 32. Now this is in a form where we can solve it. What do we do first? Add 8 to get 5x equals 40. And then we divide by 5. X equals 8. And of course, this will be the last time I do this, but we can put that back in if we want. 7x becomes 7 times 8 minus 8. Does that equal 2x becomes 2 times 8 plus 32. Now we have to work on both sides here. 7 times 8 is 56. Minus 8 is 48. On the other side here, 2 times 8 is 16 plus 32 is 48. So we get the same number on each side. That checks out. So there are two things we have to sometimes do before we solve. One is the first thing we should look for is if we can combine on either side. Second is get the variable on only one side. That's like the second one. And then we can do the solving. We can take it apart. So we might have something like 5x plus 7 plus 3x equals 4x plus 21. Oops, that's not going to work. Let's do 4x plus 35. So here on the left side, we can combine, what can we combine? 5x and the 3x to make 8x plus 7. On the right side, there's nothing to combine, so it's just 4x plus 35. So that's step one. Next, we have to get the variable on one side by subtracting 4x from both sides to give us 4x plus 7 equals 35. Good. This x has been taken away, it's gone. Now we're ready to solve. Our first step would be to subtract 7, you got it. 4x equals 28, and then divide by 4, x equals 7. Perfect. Well, you guys seem to be pretty good with the algebra. So let's take the next step then, since we're having fun with it. Something you remember from algebra? Well, that's a good thing. So 3 times 5x minus 7. Of course, the thing we see here that's different is the parentheses. Whenever we see parentheses, it should scream at us to do something here first. Here we're going to multiply. We should always check, is there anything we can do inside the parentheses? No. So then we should check if there's anything needs to be done to the parentheses, and that is multiplied by 3. So we distribute. 3 times 5x is 15x. 3 times negative 7, negative 21, equals 39. Now we're ready to solve. We've combined everything, and the variable is on one side, so we will add 21 to get 15x equals 60. And then divide by 15 to get x equals 4. Perfect. Oh, sure. Yeah, that's my bad handwriting. Oh, sure. Let's do something like this. Where do we start? Parentheses. Anything to do inside them? No. 2 of them times the 7. 7 times 2x? 14x. 7 times negative 3? Negative 21. Now we still have the plus 4 here is outside the parentheses, so it does not get multiplied. But it is still there. Are we done combining? No. Yeah, we have the negative 21 and the positive 4. So the 14x doesn't change. Negative 21 plus 4 is a negative 17. You got it. So 14x minus 17 equals 53. We'll add 17 to both sides. 14x equals 70. Perfect. And then divide by 14. X equals 5. Now, I haven't done it these last couple of examples, but like I said, you could always go back here and say, okay, well, if x is 5, that's 7 times 2x becomes 2 times 5 minus 3 plus 4 equals 53. Well, the right side is 53. We do our order of operations to make sure the left side is 53 as well. Of course, they can get worse than that. Let's look at something like this. 12 minus 3 times 5x minus 28 equals 6. So now we see the parentheses here. Nothing to do inside them, so we're going to multiply by, good, the negative 3. So the 12 doesn't change. We have negative 3 times 5x is negative 15x. Negative 3 times negative 28, positive 84. Are we done combining? No. 12 and 84 make 96, right? So we've got the negative 15x, and that's going to be a positive 96. We'll subtract 96 from both sides. Keep that thought. We'll come back and I'll show you how to do that. It'll still work out. So if we subtract 96 from both sides, we get negative 15x equals negative 90, and of course we would have to divide by a negative 15, not x, just negative 15, right? Giving us x equals positive 6. Negative divided by negative is a positive. So back up here, we had negative 15x plus 96 equals 6. The question was, what if we don't like working with negatives, what if we add 15x? Well, we do it to both sides. So on the left side is gone, we just have 96. On the right side, 6 plus 15x have different names. So that is just 6 plus 15x. Now we would subtract 6. 90 equals 15x. And then divide by 15. You got it. So we still get 6 equals x, or x equals 6. This maybe took an extra step or so, but again, if you don't like working with the negatives, that is a good way to do it, to make sure you're not working with negatives. Starting to feel close to it, you're right. It's just a second here, I'm a little off on that. There, that's what I want. Now we will come back next week and do more examples of this. Well, we'll make it worse, don't worry. If you haven't learned yet, I always make it worse. It's kind of my job. I used to tell people, if you walk out of my room every time feeling good about yourself, I haven't done my job. So anyway, on the left side, let's combine what we can combine. On the left side, what can we combine? Can we do anything in the parentheses? No. So we're going to multiply by the 5. What's 5 times 7x? 35x. What's 5 times negative 6? Negative 30. Now the negative 5 is not in the parentheses. It does not get multiplied. Now we're going to stay on the left side. Can we combine anything more? Yes, the numbers. So this is 35x minus 35. Now there's no more to combine on the left side. So let's look on the right side. So nothing in the parentheses, so we will multiply by 3. What's 3 times 4x? 12x. And 3 times 2? 6. Now again, the 9x and the 1 are outside the parentheses. They do not get multiplied, but they are still there. Now what else do we combine? 12x and 9x make 21x, and then we also have 6 and 1 makes 7. Now we've combined everything we can combine. It's time to get the variable to one side. So we'll subtract 21x, which gives us 14x. Perfect. On this side, the 21x is gone. So 14x minus 35 equals 7. Add 35. Good. So we have 14x equals 42. And then we divide by 14. Yes, x equals 3. I think we've had enough for one day. Also in the big book, actually I have to get you, Lexi, could you look for me? It's about page 380. It's the unit review for chapter 14. Let me know exactly what page it is, if it's 380 or 381, 379. So it would say unit exercises on it, so it might be the page after that. So there it is at the bottom of page 3. So page 380 and 381. Unit exercises. 1 through 47, the odd. Then my other page numbers here, I believe. Yeah, we'll call that good enough for now. If you give me 4 minutes, you guys don't have your books with us, do you?